Now let's consider a well that is not infinite, but has a finite height, so that in the middle, the potential energy is still zero, and at the edges, the potential energy is greater than zero. It's mu naught. Well, now let's take a look at Schrödinger's equation. Before, the potential when we were at an x of less than 0 or greater than L was infinite. So the only way to get this equation to come out to be 0 for an energy that was not 0 was for the wave function to be 0 outside of that well. Now, the potential energy is not infinite outside of the well, so I can have a little bit of a derivative here that will cancel against E multiplying a wave function. In other words, the wave function is allowed to go into this region. Now, in order for it to be a confined particle, the total energy has to be less than the potential energy at the sides. That means that the energy minus the potential energy is going to be negative. And that means instead of having an oscillating solution like we had in here, we're going to have an exponentially damped solution. So this is what the solutions look like for a certain finite height well. We have a probability distribution very much like the one we had before inside the middle of the well, but on the outsides we have a wave function that is exponentially damped but does not go immediately to 0. As the energy level gets higher, as the particle gets closer to the surface of the well, the probability of being found inside the wall here, of escaping outside the wall, is greater, so the wave function penetrates further in. Here's the case that is starting to get near the actual top of the well, and we penetrate quite a ways into the walls. Notice, this is not an idea that exists classically. The energy minus the potential energy is the kinetic energy. Classically, if you're in a region where the energy is less than the potential energy, you would have to have a negative kinetic energy, which doesn't exist. But quantum mechanically, we can have these exponentially damped wave functions which correspond to a negative kinetic energy. So here we have an energy diagram for this finite energy well. In this case, the energies drop down a little bit compared to what they would have been in the infinite well. The reason for that, this wave gets to stretch out a little bit as it penetrates into the two walls. So the energies are a little bit suppressed. They have slightly lower momentum because of slightly longer wavelengths. And they don't follow exactly an n-squared pattern. So notice this one isn't exactly 4 times this energy level, and this one isn't exactly 9 times the original energy level, although they're not that far off deep in the well. Another interesting thing that happens is that we don't get any quantized energy levels for energies that are greater than the top of the well. And the reason for that is that once you're up there, you're going to have a positive kinetic energy whether you're above the well or to either side of it. So here we're in what's called the continuum, the region where the particles are not confined, and since they are not confined, they don't form standing waves and don't have any limitation on the energies they can take.